So in the previous class we had started with this Z transform, right? So what was the formula for Z transform? Much simpler than your the Fourier series symbol. The formula is very simple. It is x of n z to the power minus n for all the non-zero values that it exists. Okay. So we saw 1 2 3, right? We saw yesterday three finite duration sequences, and it turned out that all of their ROC was entire z plane except only at 0 infinity and so. Then we saw one more numerical, right? What was it? Alpha to the power n into u of n. Then we saw this alpha to the power n into u of n. Okay, everybody is seeing this PPT, right? Whatever I have done. I hope I'm sharing the right screen. Okay, okay. So alpha to the power n into u of n. You remember this question, okay? X of n equal to alpha to the power n into the u of n. It always gives you a z transform. Z divided by z minus alpha. Okay. So remember this particular problem as a template. Okay. Alpha to the power n into u of n gives you a z transform. Z divided by z minus alpha. Remember these, this template. We will use it every time. If at all there is a 1 by 2 to the power n into u of n coming, we will straight away conclude that its z transform is z divided by z minus 1 by 2. If at all 0.5 or 1 by 8 to the power n into u of n comes in, its z transform, straight away conclude that z divided by z minus 1 by 8. Magnitude z greater than alpha. If at all it is half to the power n into u of n, magnitude z will be greater than 1 by 2. Above 1 by 2, all values will be converging. Okay. This is one template, and second template that we are going to use is this one. Which one? The next question what we saw, right? Minus alpha to the power in u of minus n minus 1. For this one also, the z transform is going to be z divided by z minus alpha, magnitude z less than alpha for ROC. Okay. These two templates you will use all the time so that we don't have to solve the problems each and every time. And one more thing that I want you people to know is whenever the ROC is determined at the locations of infinite sum, ROC is never determined by the Z transform, but it should be determined somewhere here where we do the substitution, okay, at the early stage. Okay. And one more observation that you could make is when the signal was right sided, right? When ROC was right sided, and the signal was right sided, ROC there was outside the circle. Remember, here the signal is left sided, here ROC is inside a circle. Just remember that. Okay, just remember that. Okay. So today we'll see a few more numericals. There are several of those. We'll see only the one that matter to us. Okay. Yeah. This one here. Okay, now all of you I hope are listening. So let us go to this particular numerical that we have on the screen. So what sort of numerical is this, by the way? It's a combination of the template. You can see this one here is a right sided signal, whereas this one here is your left sided signal. Okay. This one is right sided, this signal is left sided. Okay, so can you guess the Z transform of this, by the way? Can you guess the Z transform here? You can see what we'll do here. We will not go and try to solve with the formula. Rather, I would say this Z transform is what was it? X of Z, the formula. Let me go back to the previous one. Let me go back to the previous numerical and show you. Have we done alpha to the power n into of n? No, but we have done alpha to the power n into of n. So it is z divided by z minus alpha, magnitude z greater than alpha is the case, right? So similarly here for this particular case, I am going to get z divided by z minus 1 by 2. Z minus 1 by 2, and my ROC is going to be magnitude Z greater than 1 by 2. Okay, so it's going to be a circle of radius 1 by 2, and ROC is going to be greater than 1 by 2. Okay, for half the term only. Okay, I'm telling only for the second term. Okay. So this is how it is going to be for this particular term. What about this particular term? You remember this, right? Minus e to the power n u of minus n minus 1. Here also it is same. Z divided by z minus what? So what was the template? Minus alpha to the power n u of minus n minus 1. In place of alpha we have 1. So this is z divided by z minus 1. And ROC for this case is, it's a left sided signal. So ROC is going to be inside the circle, right? ROC is going to be inside the circle. The circle of radius, how much? The circle of radius 1. Okay, it's the circle of radius 1. So their combined ROC, this and this, what it is going to be? Now let us see. I just wanted, as I told you, make sure you have a scribbling pad so that it gives you a good feeling, right, when you solve it ahead of the PPT. Yeah, here it is, right? So yeah, we have done this. Okay, okay. Now see here. ROC for the first signal, it was greater than 1 by 2 for this first one here. Okay, for first signal was left sided, right? See here, z divided by z minus alpha. This would have given me z divided by z minus alpha. So for the first signal, ROC was outside a small circle of radius 1 by 2, and for the second here it is outside this. Okay, and for the second signal here, see this term here turns out to be z divided by z minus alpha only. Okay, but for this signal ROC, since it is left sided signal, ROC is going to be inside the circle of radius 1. Okay, ROC is going to be inside the circle of radius 1. So where does it overlap? Here it overlaps between 1 by 2 and 1. So there are two circles. One is of radius 1 by 2, another one is of radius 1. So ROC lies in between. ROC lies in between the two circles. Okay, in here also it is unstable. Outside the circle of radius 1 also it is unstable. Okay, got this thing? Okay, so that was interesting. Okay, next now let us see any other type of numericals. Okay, okay. So yeah, this is the numerical that we spoke about. Now consolidate. So what happened here, by the way? See, this was the template, z divided by z minus 1 by 2. Here also, anyway, this is also fine. Yeah, somebody. Okay. Yeah, so this is half to the power n into u of n. It was here. So for first signal it varies from 0 to infinity. For signal it is minus infinity to minus 1. We have done this thing yesterday. Okay, so it's 1 minus 0 to infinity. Okay, so it's the same. Okay, and finally there is the ROC. You can see whenever the ROC is a combination of a right sided signal and left sided signal, it is going to be a concentric ring. Okay, ROC is a ring within the ring. ROC will be in between the two rings. Okay, okay, that's that. So now let me take a set of three signals. Let me take three standard questions. These are okay, very interesting and also important also. Okay, let us see. All of them are a combination. You can see this first signal here. The first signal here is, what is the nature here? See, this one is right sided. Okay, 2 into half to the power n into u of n. This signal is right sided, whereas this signal is u of minus n. The moment you say u of minus n, it is left sided signal. Okay, now what about this one here, by the way? Say this one, 2 into half to the power n into u of n. This signal is right sided, whereas this particular, what about this? Do not get fooled by this 1 by 2. Okay, you see this particular thing, this is u of n. So this signal is combination of two right sided signal. The first x of n was a combination of a right sided signal and a left sided signal, where the second one here, y of n, is combination of both right sided signals, whereas this third one here, you can see this also u of n, this also u of minus n. So this first sequence is also left sided, second sequence is also left sided. Okay, now what do you think will be the ROC in each of case? Now we are in a stage here, we can always determine the z transform here. Can we guess the z transform here? Is it a big deal? We will see the first problem here. Okay, what about the ROC? Let us see each of this. each of these problems. Okay, so what we are trying to do here is we are trying to predict the nature of ROC by looking at different types of numericals. Okay, okay, let us go ahead with the first one. Let us choose this first one where first sequence is left sided, whereas the second sequence is right side. Let me tell you, a Z transform is also linear in nature. Okay, see, if at all you can visualize a signal as sum of two signals, the individual Z transform can be added up to give you the complete X of Z. Okay, okay, now let us see the first signal here. Okay, so what is the signal? Half to the power n into u of n. Now see this particular problem here. So alpha to the power n into u of n gives you z divided by z minus alpha. Remember, alpha to the power n into u of n gives you z divided by z minus alpha. ROC, right, greater than alpha. So here also it is same. So for first signal, from the template, its Z transform is Z divided by Z minus alpha. 2 was a constant. It simply gets multiplied here. Okay, here outside the bracket. Here also simply gets multiplied. Magnitude greater than the, what is the case? Alpha here. Alpha here in this case is 1 by 4. So here you can see the first thing, it is greater than 1 by 4. Okay, for first signal ROC is greater than 1 not first signal, sorry, the second signal here, right? We took it because it was right side. Okay. Now what about this signal here? What about this signal here? Now here we need to substitute. Here we need to substitute. Okay, here we cannot use the ready formula because there is a minus sign here. There's a minus sign here. So for here we will substitute. Okay, since this is u of minus n, so how does this signal would look like? This signal would look like, it is not the signal which is going to see here. See here, let me take you to the previous numerical which we saw. Here, see here, this signal was minus of u of 1 minus n minus 1. Now this signal was something like this. It was starting from minus infinity and ending at minus 1. Okay, and all amplitudes were negative. Okay, whereas the numerical which we have right now, this one here, which one? Okay, sorry. Now this numerical here, this is not that signal. This is a simple left-sided signal which starts from 0. It starts from 0. It is having alternative minus signs. Yeah, it's having alternative minus signs. That is also there. I think it's growing also, right? Yeah. This is not decaying. Moreover, this is a growing exponential on the left side. But one thing is for sure, we are not bothered. We are only bothered about its, from where to where, alternating signs. Okay. So here you can see the limits are for the first summation. The limits are from minus infinity to 0. The limits are from minus infinity to 0. Okay, let us change the limits only for now. Let us keep this thing aside. We know the answer of this. For this particular thing, it is z divided by z minus alpha. 2z divided by z minus 1 by 4. We are done with this. This one will bother. We will change the limits. Let us put n is equal to minus, or k is equal to minus n. So this entire thing comes in numerator because of the minus sign. Now here, yeah, limit, yeah, should I any query it was, or okay, I will disable this participant annotation. Okay, okay. Sorry for that. Yeah. So the limits you can see minus infinity to 0 because the signal was starting from minus infinity ending at 0, unlike the previous one. Then we change. Let us put k is equal to minus n. Let us put k is equal to minus n. So what's going to happen? This n is going to become minus k. This is going to 0 to infinity. Minus, let us absorb the minus inside this so that this comes to be 2 minus 2z to the power minus 1. So it comes in the numerator. So that minus 2z whole to the power k. And what's the answer for this theorem? 1 divided by 1 minus alpha. So you can see some term alpha, summation 0 to infinity is 1 divided by 1 minus alpha. Then minus sign here is the reason for this plus. Okay, and is the reason for this plus. Okay, okay. So That was that. So one signal right sided, another signal left sided. So where do we determine the ROC now? Where do we determine the ROC? Once again, let me tell you, ROC is determined at the points where there is an infinite summation and all the terms are inside a bracket of an n. Now tell me, this thing would converge only when this particular term 1 by 4z, this term, the first term would convert only when this particular entire term is less than 1, right? Otherwise, if this term was greater than 1, it would have simply diverged. So what this tells? So this implies magnitude z greater than 1 by 4 as expected, right? Z divided by z minus alpha, magnitude z greater than alpha. Okay, outside the circle, outside the circle of radius 1 by 4. Whereas for the second signal here, you can see either this one or this one. See, this term should be less than 1. Minus what is it? Okay, okay, yeah. So for this particular term, it is minus 2 z, right? Minus 2z. Okay, what is the magnitude of minus 2z? What is the magnitude of minus 2z? Magnitude of minus 2z will be 2z only. So here 2z should be less than 2z should be less than 1. So what is the condition for z then? What is the condition for z? That means the condition for magnitude z would be what is it? The z will come on this particular side. So it should be greater than, smaller than or greater than magnitude z smaller than 1 by 2, right? Magnitude z smaller than 1 by 2. So here is our ROC. For right sided signal, outside the circle. For right sided signal, it is outside the circle, outside, okay. For left sided signal, it is inside the circle, okay, inside the circle. And for the entire case, it's the intersection of both. So outside 1 by 4, all the values, first one is stable, outside 1 by 4, all the values. Here also, first term is stable, here also this particular, but second one is stable only inside 1 by 2. Okay, so where does it overlap? It overlaps only in this particular path, okay. In first case here, the first term doesn't converge, here the second term doesn't converge. So my ROC is a circle. My ROC is a circle. So one signal is right sided, another signal is left sided. My ROC is a concentric ring. Okay, okay. Now let us go to the next problem. Okay, first problem, one signal was left sided, another signal was right sided. Okay. Now let us see the next problem. Here what is it? Both the signals are, first signal is also right sided, second signal is also right sided. So right signals are quite easy, right? So here also we'll use the template z alpha to the power n into u of n. You can see alpha to the power n to u of n, z divided by z minus alpha, z divided by z minus alpha only, with a 2 getting multiplied. Here also z divided by z minus alpha, alpha is minus 1 by 2. So this is it, this is it. So for the first case, it is magnitude z greater than 1 by 2. See, you can see for first case magnitude z greater than 1 by 2. For second case, magnitude z greater than 1 by 4. So the combined ROC, where both of them will be stable, by the way. So in this particular case, here in this smaller circle, only one of the term is converging, second term is not. Whereas outside 1 by 2, both the terms, okay, both the terms converge. Okay, so when both the signals are right sided, ROC is outside the outermost circle. Okay, ROC is outside the outermost circle, or shall I say outside the outermost pole. You see here, you see the poles here, you see the poles here. See, there was a pole here, there was a pole here also, right? How do we get the poles, by the way? Substitute the denominator to 0, right? How do we get the poles, by the way? For to get the poles, you should have both numerator and denominator in terms of positive powers of z. You equate the numerator to 0, you get zeros. You equate the denominator to 0, you get the pole. Here you can see ROC was outside the outermost pole when both the signals were right sided. Okay. Okay. Yeah. Now let us see the third type of problem. Third type of problem. Here you can see both the signals are left sided. This signal is also left sided. This signal is also left sided. So just like in the previous case, what we did, we will change the limits and we get this particular answer here. We get this particular answer here. Substitute the denominator to 0. We will get whole set 1 by 4 and minus 1 by 2. Okay, ROC, since both the signals were of left side, here you can see ROC of this one minus magnitude. I will not write minus once again, magnitude 2z. This should be less than 1 or magnitude z less than 1 by 2 in the first case, whereas in the second case it will be magnitude less than 1 by 4. So for first case it was a bigger circle with magnitude 1 by 4. Here only the first term was converging. In this particular second thing, okay, here only first term was converging, whereas here for the second case, here second was converging. Both of them overlap where, so you can see inside 1 by 4, inside circle 1 by 4, first term also converges, second term also converges. Okay. Okay. So and you can see the pole here. ROC was inside the innermost pole. Okay. Okay. Now keeping these things in mind, now I think we are ready. Now I think we are ready to determine the properties of ROC. Okay. Now we are ready to determine the properties of ROC. Now let me just take a small pause here and ask you, did you get any doubts here? Anybody? Did you get any doubts here? Any topic that is not clear? Hmm? Shall I? Shall I continue? Hmm? So what we'll do now is, we have seen several types of numericals here now, and these many numericals are sufficient for us to now conclude the properties of ROC. Okay, now shall we go and see the properties of ROC? What do you think are the properties of ROC here? So the first property of ROC, the region of convergence, you can see ROC here is a connected region. Okay, so we saw it. Okay, ROC is always a connected, wait a second. Okay, ROC is a connected region. Are we convinced with this particular statement? ROC being a connected region? Yes, I guess, right? Because you can see connected region is when ROC is not a point. Okay, ROC is never a single point. Okay, ROC is a whole region. Okay, that's what the author is telling. You can see in all of these cases, maybe ROC is a entire region. You can see it's not a single point, only here, only here, only, no. It is just like your Laplace transform, right? So in your Laplace transform, you do the stability, right? What do they say? If at all there is some what see left side of this particular thing, this entire area you say is a stable, right? So something like this. So this region of convergence is always a connected region. It's never been a point. Exceptions, right? We said except z equal to 0 or except at infinity, otherwise it is always a connected region. Okay, okay, the first statement does make sense. Okay, so what is the first property of ROC? ROC is a connected region. What is the second property? ROC does not contain any poles. Okay, ROC, yeah, this one we are convinced. ROC does not contain any poles. Now let us see what is the definition of a pole, by the way. What is the definition of a pole? Hmm? What is the definition of a pole? Okay, what is meant by pole? Poles are, now see here, let us take this example. Let us take this particular example here. Okay, here. So what is meant by a pole? See, if at all I substitute this z equal to 1 by 4, right? See here there is a pole, okay. If at all I substitute z equal to 1 by 4, so what's going to happen? This is going to be 1 minus 1, 0, right? The moment you substitute a pole, this entire term goes to infinity. Whereas what is the definition of ROC? ROC is those values of z for which x of z is going to be stable, okay. So ROC can never contain poles, because poles are those values which will make entire x of z goes to infinity. So ROC can never contain poles. Is it true, by the way? Let us see all the problem. Now see, here we have the ROC. Here we have the ROC. Okay. Does it contain poles? Are there any poles inside this? No, no, no. Poles are on the boundary. Okay. Poles form the boundary of ROC, but they are never inside the ROC. They may be outside the ROC, or they may be on the boundary. There may be zeros inside the ROC, but poles will not be there. Any other problem? Let us see. Okay, okay. Let us see. Go through all the problem. This one problem here, uh, this one here. Now this here, does it contain any pole? The ROC here, the shaded area is ROC. Does it contain? No, no. Here the boundary, it is there on the boundary. It is there inside, but not on in the ROC. See, this is not a stable region, right? Here it's not in the shaded area. What about this one? Okay, okay. Here, is there any pole in the ROC? No, no, no. There is no pole, but it is from the boundary. You can see 1 by 4 was a boundary. 1 by 2 is also a boundary, but not everywhere. Not everywhere. Okay. So even in all the numericals that we see, except probably, okay, okay. Now this is an exception. See, as I said, for this particular case, except 0. Okay, this is just a point. This is just a point, and ROC does not contain uh, pole. Okay, ROC is entire z plane except origin. That is the only case. Otherwise, anywhere you can see all the problems. Okay. So the second property of ROC, I think we are all now convinced. ROC does not contain any poles. Okay. ROC does not contain any poles. ROC is a connected region. Okay. The third one. ROC of a finite duration signal is entire z plane except for origin or infinity. Except for origin or infinity. Is it so? ROC is an entire, what is it? What is it? Um, what is the statement? ROC of a finite duration signal is entire Z plane. Have you seen any? Now see here. Now let us go back to the problem. This signal here, infinite duration, infinite duration. I have not solved this. Okay. I will do it in the extra time. Okay. If at all you are interested. Okay. Now see here. What sort of signal is this? Infinite duration. Infinite duration. ROC, a confined duration. Okay. Now this one here, you can see infinite duration, ROC, not entire z plane, only certain region. Okay. Here also in both infinite duration, except for the first three problems. Remember, you can see x of n is equal to u of n. Here also outside a circle. Here you can see delta n plus k, only one impulse, ROC, entire z plane. Okay. The first three problems, that is, you can see finite duration 1, 2, 3, 4, ROC, entire z plane. The first problem ROC was entire z plane. So except for this first three problems, in all three problems you can see x of n was finite duration, so ROC was entire z plane, except for, right, in the first signal what I gave, except for z equal to 0, except for z equal to 0. In the second signal, except for z equal to infinity. For this third signal, except for 0 or plus or minus infinity. So in all other cases, you can see it's not entire z plane, but it is confined to certain region. So what is the conclusion? The third one, ROC of a finite duration signal is entire z plane except for the inclusion or exclusion of origin or infinity. Okay, are we convinced with the third property? Yes. ROC of a right-sided signal is outside a circle. Is it so? Alpha to the power n into u of n. What is the z transform of alpha to the power n into u of n? ROC of a right-sided signal is outside a circle. ROC of a left-sided signal is inside a circle. Are we convinced with this thing? Are we convinced with this thing? Let us see. Let us see. ROC of a right-sided signal. You can see u of n. This is a right signal. ROC is outside the circle. Okay. Now any other? Here. here. ROC you can see of a right side U of n. ROC of a right sided signal is outside the circle. You can see this one is a right sided signal. So ROC is outside the circle. Here it's a left sided signal. So ROC is inside the circle. Okay, ROC here is inside the circle. Any other yes, this one left sided signal ROC is inside the circle. Now this one right sided signal ROC is outside the circle. Okay, so this property also I think we are sort of convinced. ROC of a right sided signal is outside the circle, ROC of a left sided signal is inside the circle. ROC of a both sided signal is a concentric ring bounded by the poles. Is it so? ROC of a both sided signal. We have seen ROC of two sided signal. Just now we saw three signals, right? If at all signal is two sided, if at all the signal is two sided, it can be a concentric ring. See here, which is a two sided signal here? Only the first one is a two sided signal. See, this is right side, this is left side, and here our ROC turned out to be, rightly a concentric ring, right? ROC turns out to be a ring within a ring bounded by the poles. You can see outside this particular circle there is a pole, inside this circle is also pole, and this pole is defining the boundary. Any other? Yeah, here also poles are there on the boundary. Okay, so we are quite convinced. Yes. Then finally, what is this particular thing? ROC of a stable system includes a unit circle. Okay, now what is this thing? ROC of a stable system. What is a stable system? Now, what is a stable system? Now, let me, tell me, x of n is equal to, not x of n, sorry. H of n is equal to alpha to the power n into u of n. You have studied stability, right? Now tell me, is this thing stable? This thing is stable for magnitude alpha less than 1. If magnitude alpha is greater than 1, this is for here. For magnitude alpha less than 1, this is stable. Magnitude alpha greater than 1, this is unstable, right? Now what is the ROC here? See, ROC is outside alpha, right? ROC is outside alpha. Okay, now, if at all this is stable, now let me draw a unit circle here. Okay, now let me draw a unit circle here. Let me draw a unit circle here. Okay, let me draw, say this is my unit circle of magnitude. Okay, poor handwriting, sorry for that. Okay, now here let me draw a unit circle. This is circle of magnitude 1. If at all I say my signal is 0.5 to the power n, 0.5 to the power n into u of n, it is stable, right? Half 0.5 is less than 1, so this is stable. So my ROC is a small circle of radius 1 by 2, and it is outside the circle. ROC is outside the circle. Now my ROC here, you can see it contains this unit circle, right? If at all I have a signal 2 to the power n into u of n, if at all I have a signal 2 to the power n into u of n, then what's going to happen? Is the signal stable, by the way? 2 to the power n into u of n, no. 2 to the power 0, 1, 2 to the power 1, 2, 2 to the power 2, 4, 8, 16, 32, no, it's unstable. So, if at all I have my unit circle here at radius 1, 2, ROC in this particular case will be outside 2, right? See, this is circle of radius 1, whereas this one is radius 2. So, here you can see the ROC. So here you can see the ROC does not contain. Okay, okay. Nobody can see the screen now. Is it? Sorry. One second. Okay. Once again. Sorry for that. Yes. 0.5 to the power n. 0.5 to the power. Okay. Mhm. Okay. Now I think it is fine, right? Okay. So now let us take the case. Okay. Anyway, let me not draw this. So now here, let me go to numerical only. Let me go to a numerical only. Do we have any? Yes. Now here you can see. For this particular signal here, 1 by 4 to the power n into u of minus n. No, this is a bad tough signal. Alpha to the power n into u of n. Now let me take two cases. Okay. Say half to the power n into u of n. Half to the power n into u of n. This is having my ROC. This is having my ROC outside. This is having ROC outside 1 by 2. This is having ROC outside 1 by 2, and it does contain the unit circle. It does contain units. Anyway, anyway, the time is running out. Let me stop here. Tomorrow we'll once again revise. You can go through all these problems. If at all you're interested, I will start one more session now of 10 minutes where we'll see this in detail. Interested students can join in that session where we'll once again revise this ROC, and we'll see three more problems that are there. Okay, I will share the link. If interested, you can join. Okay, let me stop here. It will